then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. It's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well are able to use that 3D model, enter the terrain and make decisions with a much better understanding of the context. We're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. There's the flag, there's the cut of the rock, and the other cuts. Now on Mars, it's a different scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations of in OnSight is we started combining rover imagery from multiple rover positions. So if the rover is parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and get a more complete model of that rock than from any one position, on its own. And the holy grail of this is to take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high quality 3D imagery all the way. So OnSight was started in the context of the Mars rover missions, but the capability that OnSight and tools like it provide is really, it's a virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in Western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field. So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public, so the whole world gets to go along, for the ride.
So I've never been here before, and the landscape in this environment is just, my mind has been blown being out here for a couple of days. I mean, the scale of the glaciers, the complete lack of vegetation in this area, other than sort of, lichens and moss. It's kind of an otherworldly place. It's really starkly beautiful. I think in terms of why anybody should care about these rocks, I mean, they are the record of some of the oldest processes occurring on our planet. I mean, there are very few places that preserve rocks this old, and so they're really a precious resource for geologists to understand what was going on the Earth, close to, in its infancy. So it's an important and special place.
I will gain a huge insight into these particular rocks, but it will also increase my understanding of how you actually demonstrate that something is or isn't a biosignature that I will apply in all my other work.
It's the ability to minimize the ambiguity before it even gets to the publication, minimize the ambiguity and minimize the bias. When it gets out into the press, it's going to be that much more considered, that much more robust. I think that's what's the best outcome of this workshop.
To observe with Hubble, we actually have to plan out pretty far in advance. And for the outer planets, what we do is we pick the time when they're at opposition. And that means that it's opposite from the sun, from the Earth's point of view. And that basically gives us the highest resolution view. That's when Hubble is the closest to each planet, even though that doesn't vary much over a year. And the planets are a little bit more challenging because they move. And so Hubble has to find guide stars first that tell it where it's pointing in the sky, but then it has to track those planets. So it has to move following the planet across the sky. And so that has to be interleaved with all the other science program Hubble is doing every single day. And so it's very carefully coordinated to fit in as Hubble then orbits around the Earth. And so it gets planned out down to the minute of exactly which image we're going to take in which filter for each of those planets. So it's a cosmic dance of getting Hubble pointed in the right place, moving in the right direction, and tracking all at the same time. The OPAL project, or the Outer Planets Atmospheres Legacy Program, is an observational program using the Hubble Space Telescope. And what we're doing is we're looking at each of the outer planets every year so that we can build up a time base using the exact same facility and the same instruments, so we can actually track what's changing over the years on each of those planets. And it started really with Jupiter. In essence, we were trying to look at the weather on Jupiter. And as we're trying to understand weather, we know even here on Earth it changes every minute, every hour, every day. And we didn't have that kind of time coverage, but we also didn't even have long time coverage to look at things that changed over seasons. And so we had this big gap in our knowledge where we just weren't getting frequent enough data to be able to trend any of these things. And the idea kind of came about to look at a legacy program where we built up a legacy for Hubble within the planetary community. And in 2014, we started with our first observations of Uranus. And the first thing I think we noticed was Uranus had a very prominent polar cap. It was very much brighter and getting brighter over time. We've watched it over the last few years get much brighter. Neptune, on the other hand, has been really quite interesting. The first thing we noted was it had a lot of bright white clouds, and they were coming and going pretty rapidly at a lot of different latitudes. And so when we start looking at Neptune and Uranus as dynamic planets with changing atmospheres, weather, like we know now for Jupiter and Saturn, we realize that we have a lot of gaps in our understanding. And so we've been able to use the OPAL program to track how much cloud cover we have from year to year. But the other thing we can do with Hubble that we can't really do any other way is look for dark spots. And so the Great Dark Spot was this big iconic feature we saw with Voyager. And when we looked again a few years later, finally when Hubble was online, it was gone. And that kind of surprised us because we were used to the Great Red Spot, which doesn't go away. It's changed over time, but it's still there. And so these storms are not quite the same as what we see on Jupiter because they form and go away on much more rapid timescales. The latest image of Neptune is really interesting to me because we don't see those bright white clouds we've been seeing the last few years. As a matter of fact, the only thing we see in that particular image is this great dark spot. And so in a lot of ways, it brings us around full circle because this looks so much like the Voyager image from 1989. And that was pretty surprising to me, not to see as much cloud activity as we've been seeing in previous years. The OPAL team is actually a fairly small team. There's only 3 of us, but our data is immediately available to the public and any other scientist that wants to use them. And so we do that as well as our own scientific analysis. I think having so much Hubble data now, there's just so much in there to study. And, as a scientist, that's what drives us, is trying to solve mysteries, trying to look for new mysteries. And so having these long-term data sets with just such rich numbers of features in there, there's always something to go look at. And it's certainly going to keep us busy for years to come, even when we're not getting any more data.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the ONC. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module, such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks.